What's up YouTube? Chris Bandy here. In this video, I'm going to show you how to understand meter and tuplets. If you have any questions, read the description before commenting. Start by forgetting everything you know about everything. We're going to talk first about segments. How do we define a segment? All you really need is a starting point and an ending point. And if we have two segments next to each other, then the ending point of the first one will be the starting point of the second one. For example, if I want to define these segments, all I need to do is list their starting and ending points. So if I just say 0, 3, 8, 12, then I've defined all three segments. Now, how does this relate to music? Well, if we view a measure as a segment, then all we need to define a group of measures are their starting and ending points. Now, the time signature of a measure tells you how many whole notes are in the measure. Let's take a measure of 4/4. Since 4 divided by 4 is 1, this measure has a length of 1 whole note. To easily define three measures in 4/4, all we need to say is 0, 1, 2, 3. We can also view notes and rests as segments. All we need are their starting and ending points. The only difference is that we need to be able to differentiate between notes, rests, and bar lines. So let's put a B before every bar line number and an R before every rest number. So, the three types of items are notes, rests, and measures. Now let's talk about dotted rhythms. Putting a dot on a note or rest makes it longer by adding to it 1/2 of its original length. For example, a dotted quarter note is the same length as a quarter note plus an eighth note. 1/4 plus 1/8 is 3/8. So we can analyze a dotted quarter note as a 3/8 note. Now, putting an additional dot adds only half of the value that was added previously. So, since putting the first dot adds a value of 1/8, putting a second dot adds a value of 1/16. So a double dotted quarter note has a value of 1/4 plus 1/8 plus 1/16, which is 7/16. You can add as many dots as you want, and the length will keep increasing, but it will never actually reach the length that is twice the original length. Now let's talk about tied values. A tie simply connects two notes together, so that they are basically one longer note. This is a good idea when there is no other practical way to write the desired note. For example, let's take a half note tied to an eighth note. There's no practical way to express this type of note without using a tie. However, we can express this type of note with a number. All we have to do is add the tied notes together. 1/2 plus 1/8 is 5/8. So we can analyze this example as a 5/8 note. Now let's talk about meter. We've used the terms time signature and meter. What's the difference? Well, they are interchangeable, but meter focuses slightly more on how the music actually is, whereas time signature focuses slightly more on the symbols you write to express this. One way to say this is that the time signature tells you what the meter is. Now, in some meters, the bar lines won't always be on whole numbers, like 1, 2, or 3. The bar lines could be on fractions too. For example, let's take the time signature 12/8. 12 divided by 8 is 3/2. So to define one measure in 12/8 meter, all we need to do is write B 3/2. If the time signature is 7/10, all we need to do to define one measure is write B 7/10. Now let's talk about how to analyze rhythms. If we want to define a quarter note rest, another quarter note, and then a half note, obviously tied across the bar line, all we need are their starting and ending points. The first quarter note starts at the beginning, so we can put a 0. As you can see, it looks like there's a space between B0 and 0. For practical purposes, we will not consider this space as a segment. All it means is that both the first measure and the first note begin at 0. Now, a quarter note, obviously, has a length of 1/4 of a whole note. To find the ending point of any note, just add together the starting point and the length. The starting point is 0 and the length is 1/4, so therefore the first note ends at 1/4. Since the rest starts right where the first note ends, that means the rest starts at 1/4. The rest also has a length of 1/4. Again, we can get its ending point by adding together the starting point and the length. 1/4 plus 1/4 equals 1/2. Therefore, the rest ends at 1/2, which means the next note begins at 1/2. This note also has a length of 1/4. So that means the next note starts at 3/4. Now, this note has a length of 1/2, which means it ends at 3/4 plus 1/2, which is 5/4. All of our points need to be in numerical order, so we need to write this last point after the bar line. And since it is the beginning of a rest, we need to make sure to include the R. Now, obviously, every single example we could do will always start with 0, so we'll save time by not even writing the 0. If the first measure begins with a note, we'll just write nothing for it. So the first number we do write will just be referring to the second item. If the first measure begins with a rest, we can indicate that by writing an R at the beginning of the analysis. So, in other words, we are simply abbreviating our analysis by leaving out 0 and B0 and shortening R0 to R. Now, I won't always use this abbreviation in this video. I'm just showing you that this is an easy way to save time when you're analyzing a rhythm. Therefore, we've taken these two measures and simplified them into a code of only 6 numbers. R 1/4, 1/2, 3/4, B1, R 5/4, B2. I'm calling this the C-point method of analyzing a rhythm. If you only want to define the notes, and you don't care about the last bar line, then you can just leave it out of your analysis. If you do this, you no longer need the R on the last number you write, because you're no longer saying there's a rest there. You're just saying that's where the last note stops. As we stated earlier, the 3 types of items are notes, rests, and measures. There are 2 ideas to keep in mind when indicating these items. First, each number indicates the beginning of a new segment. In addition, each number indicates the beginning of a new type of item. A note number begins a new note, a rest number begins a new rest, and a bar line number begins a new measure. Second, items can be split into multiple segments. Here's an example of splitting measures. If you want to indicate a 4/4 measure containing 4 quarter notes, your analysis is B0, 0, 1/4, 1/2, 3/4, B1. As you can see, there's only one measure, but it is split into 4 segments. Here's an example of splitting notes. If you want to indicate a whole note tied between 2 2/4 measures, the analysis is B0, 0, B1/2, B1. As you can see, there's only one note, but it is split into 2 segments. Notice how there's no analysis for the second segment of the tied note, because nothing's actually happening there. It's merely part of a note that began earlier. Finally, here's an example of splitting rests. If you have 2 empty 4/4 measures, the analysis is B0, R0, B1, B2. Technically, all of this empty space can be considered as only one rest, but the presence of the bar line here splits the rest into 2 segments. And again, the rest at the beginning of the second measure is not analyzed, because it's merely part of a rest that began earlier. To build your own meter, follow these 3 steps. First, pick a pulse. A pulse can be any note value, but it is usually an 8th note or 16th note. Second, decide how many pulses you want per measure. Third, group them together in groups of 2 and 3. Each group of 2 pulses is called a simple beat, and each group of 3 pulses is called a compound beat. If you used only simple beats, your meter is a simple meter. A meter with 2 simple beats is simple duple. A meter with 3 simple beats is simple triple, and so on. To write the time signature of a simple meter, just write the number of beats on the top, and on the bottom, write how many beats it would take to make a whole note. For example, this measure has 10 eighth notes grouped into 5 groups of 2. All the beats are simple, so this is simple meter. There are 5 beats, making this simple quintuple meter. Since there are 5 beats, we write 5 as the top number in the time signature. Since each beat is a quarter note long, it would take 4 beats to make a whole note, so we write 4 as the bottom number. Therefore, 10 eighth notes in 5 groups of 2 is 5/4 meter. If you used only compound beats, your meter is a compound meter. A meter with 2 compound beats is compound duple. A meter with 3 compound beats is compound triple, and so on. To write the time signature of a compound meter, just write the number of pulses on the top, and on the bottom, write how many pulses it would take to make a whole note. For example, this measure has 12 16th notes, grouped into 4 groups of 3. All the beats are compound, so this is compound meter. There are 4 beats, making this compound quadruple meter. Since there are 12 pulses, we write a 12 on the top. Since each pulse is a 16th note long, it would take 16 pulses to make a whole note, so we write 16 on the bottom. Therefore, 12 16th notes in 4 groups of 3 is 12/16 meter. Now, with regards to interpreting time signatures, the common practice is that every time signature where the numerator is 1, 2, 4, 8, or any higher power of 2 is interpreted as a simple meter. If the numerator is 3, the time signature is still interpreted as simple meter. But every time signature where the numerator is 6, 9, 12, 15, or any higher multiple of 3 is interpreted as a compound meter. If you used both simple and compound beats, your meter is an irregular meter. An irregular meter with 2 beats is irregular duple. An irregular meter with 3 beats is irregular triple, and so on. To write the time signature of an irregular meter, just write the number of pulses on the top, and on the bottom write how many pulses it would take to make a whole note. For example, this measure has 7 eighth notes, grouped into a group of 2, 2, then 3. Both simple and compound beats are used, so this is irregular meter. There are 3 beats, making this irregular triple meter. Since there are 7 pulses, we write a 7 on the top. Since each pulse is an eighth note long, it would take 8 pulses to make a whole note, so we write 8 on the bottom. Therefore, 7 eighth notes in groups of 2, 2, then 3 is 7/8 meter. Obviously, just writing 7/8 meter doesn't indicate how the pulses will be grouped. So if you want to be more specific, you can replace the top number of the time signature with all the groupings. So instead of writing a 7, you can write 2 + 2 + 3. This is called additive meter. This is especially helpful for something like 14/8 meter. There are lots of possible ways to group 14/8 notes into 2s and 3s. So it's helpful to replace the 14 with all the groupings. For example, 2 + 2 + 2 + 2 + 3 + 3. Now obviously that last example takes up way too much space. So let's look for a way to simplify it. If you notice, all the simple beats are together, and all the compound beats are together. 4 groups of 2 gives you 4/4 meter, and 2 groups of 3 gives you 6/8 meter. Therefore, we can rewrite this example as 4/4 plus 6/8. This is called mixed meter. If you only want this for a measure or 2, it's preferable to simply alternate between 4/4 and 6/8 on each measure. However, if you want it to last for a longer time, then this is perfectly acceptable. And you can even make it clearer by drawing a dotted bar line in each measure to show the division between the different meters that you are mixing. If the top number is not a whole number, this is called fractional meter. If the bottom number is not a power of 2, this is called irrational meter. A power of 2 is a number you get by starting at 1 and multiplying it by 2 over and over again. For example, 1, 2, 4, 8, 16, 32, and 64 are all powers of 2. In mathematics, an irrational number is any number that cannot be expressed as a fraction of integers. But in music, an irrational meter is simply any meter where the bottom number of the time signature is not a power of 2. Now, you can technically get more powers of 2 by starting at 1 and dividing it by 2 over and over again. This gives you 1/2, 1/4, 1/8, 1/16, and so on. If the bottom number is less than 1, then the meter could be called inverted meter, but this is very uncommon. Let's talk about strong and weak beats. In duple meter, the first beat is a strong beat, and the second beat is a weak beat. In triple meter, the first beat is a strong beat, and the last 2 beats are weak beats. In quadruple meter, the first and third beats are strong beats, and the second and fourth beats are weak beats. In addition, the first beat is even stronger than the third beat, and the fourth beat is even weaker than the second beat. In quintuple meter and higher meters, the first beat is the strong beat, and the strengths of the other beats depend on the composer. There are 3 guidelines for notating beats. Guideline 1. If you have 2 notes next to each other in the same beat, beam them together if you can. Obviously, if one of the notes is a quarter note or longer, you cannot do this, but beam as much as you can. Guideline 2. Never extend a beam from one beat to another beat. Keep the beats separate. Guideline 3. Every beat should have a note head on it. In other words, in a 4/4 measure, you shouldn't have a blank spot on beat 3, like this. It's better to use a tied note, like this, so that there will be a note head on the beat. A note head is on the beat when it is at the beginning of the beat. A note head that is within the beat, but not at the beginning of the beat, is considered off the beat. Now let's talk about tuplets. Again, forget everything you know, and start with this one rule. A tuplet is a length changer. All that means is that a tuplet changes the lengths of all the notes and rests that are under its bracket. Now, how does it change them? Specifically, it divides them by the number that is in the bracket. For example, let's take 4 quarter notes. Using the C-point method, we can define them with the code 1/4, 1/2, 3/4, 1. Now, if we put a 3 against 2 tuplet over 3 of these quarter notes, it is going to divide their lengths by the number in the bracket. We can get this number by replacing the colon with a division slash, so 3/2. Therefore, this tuplet is going to divide the lengths of these 3 quarter notes by 3/2. Now, dividing by a number is the same as multiplying by that number's reciprocal. So, the original length of each of the first 3 notes was 1/4. 1/4 divided by 3/2 is the same as 1/4 times 2/3. 1/4 times 2/3 is 2/12, which reduces to 1/6. So the new length of each of the first 3 notes is now 1/6. Therefore, our C-point analysis is now 1/6, 1/3, 1/2, 3/4. Let's do another example. What if we put this tuplet on only the first 2 quarter notes? Well, it's only going to change the lengths of the first 2 quarter notes. Just like last time, it will change each of their lengths to 1/6. Therefore, our C-point analysis is now 1/6, 1/3, 7/12, 5/6. So even though this looks really strange musically, it still reduces easily within the C-point framework. Tuplets can also lengthen notes. Let's put all 4 quarter notes under a 3 against 5 tuplet. Now the tuplet is going to divide each of the lengths by 3/5. Each of the lengths was originally 1/4. And 1/4 divided by 3/5 is the same as 1/4 times 5/3. 1/4 times 5/3 is 5/12. So our C-point analysis is now 5/12, 5/6, 5/4, 5/3. Now, we learned that a quarter note under a 3 against 5 tuplet has a length of 5/12. Let's learn how to go the other way. If I asked you to write a 5/12 note, how would you do it? Well, if you remember, the thing that a tuplet does is divide the lengths of the notes under it. We can express this with an equation. The normal length of the notes, which we'll call n, divided by the tuplet value, which we'll call t, equals the changed length, which we'll call c. In our example, we want a changed length of 5/12. Now, all we have to do is pick a normal length or a tuplet value. A normal length is any note that you already know how to notate. For example, we know how to notate a quarter note, so let's pick 1/4. Now we just solve for the tuplet value. Multiply both sides by t, multiply both sides by 12, reduce the fraction on the left, then divide both sides by 5. So our tuplet value is 3/5. Therefore, one way to notate a 5/12 note is to write a quarter note and put a 3 against 5 tuplet over it. Let's return to our previous example. What if we tried to notate this in a 4/4 measure? The 4 quarter notes originally filled up the entire measure. Since the tuplet is making them longer, they would spill over the bar line. In other words, we would have to tie one of the notes. So, how do we notate this? Let's recall our C-point analysis. First, since these notes will be bleeding over the bar line, that will leave some extra space for rests in the next measure. Let's go ahead and notate these rests all the way up until the next bar line. Therefore, we will need to mark the end of our last note as a rest, because a rest will begin at 5/3. Second, let's add in as many bar lines as we need to frame the entire example. Obviously, there is a bar line at 0, but we don't need to put that. The next bar line is at 1, and the next bar line is at 2. We don't need any more bar lines because now we've framed all of the notes. So, all we have to do is notate each of the segments. To find the length of a segment, take the equation we used earlier and subtract s from both sides. Now we know that the length of a segment is the ending point minus the starting point. The first segment goes from 0 to 5/12. 5/12 minus 0 is 5/12. So the first segment has a length of 5/12. We already know how to write a 5/12 note. It's just a quarter note with a 3 against 5 tuplet over it. The second segment goes from 5/12 to 5/6. 5/6 minus 5/12 is 5/12. So the second segment also has a length of 5/12. The third segment goes from 5/6 to 1. So the length is 1/6. This segment is obviously shorter because it's the first segment of the note that's being split across the bar line. Now, since we might not know how to notate a 1/6 note, let's use the equation again. Our changed length needs to be 1/6. And let's pick a quarter note again for the normal length. Then we can just solve for t. So for the third segment, we can write a quarter note with the 3 against 2 tuplet over it. Now, because this segment ends with a bar line, that means the actual note continues past the bar line. So we need to tie this segment to the next segment. The fourth segment goes from 1 to 5/4, so the length is 1/4. So for here, we just write a quarter note. The fifth segment goes from 5/4 to 5/3. So the length here is 5/12. So we just write another 5/12 note. The final segment goes from 5/3 to 2. So the length is 1/3. Now, since we might not know how to notate a 1/3 note, let's use the equation again. Our changed length is 1/3. Now, tuplets are commonly used to make notes shorter. If I pick a quarter note again for the normal length, then the tuplet will be making the note longer, since a third note is longer than a quarter note. Since that's a little unusual, I'm going to set my normal length up to 1/2. Now we can solve for t. So for the final segment, we can write a half note with a 3 against 2 tuplet over it. But since this segment is indicated as a rest, we need to write a half rest instead of a half note. So you can use this method to write down literally any rhythm, no matter how complex it is. Now we're going to talk about how people normally write tuplets. First, it's common for the left-hand number to be the same as the number of notes within the tuplet. That's because, for most people, the colon doesn't represent division, it represents the phrase, in the place of. So 3 quarter notes within a 3 against 2 tuplet really just means that there are 3 quarter notes in the place of 2 quarter notes. Second, if there's a bracket, it's proper for the bracket and the stems to be on opposite sides from each other. Third, if every single note in the tuplet is connected by a single beam, for example, with eighth notes, then it's proper to leave out the bracket and place the number back on the same side as the stems. Most people also abbreviate tuplets by writing only one number in the bracket. When there's only one number in the bracket, that's understood to be the left-hand number, and the right-hand number is simply hidden. Now, there's a simple method for figuring out what the hidden right-hand number is. If the left-hand number is a power of 2, then the right-hand number is simply the left-hand number times 3 halves. So, if you see a tuplet with only a 16, just multiply 16 by 3 halves. That gives you 24. So you know the hidden number is 24. Therefore, you know that a 16 tuplet is just an abbreviated way of writing a 16 against 24 tuplet. If the left-hand number is not a power of 2, then the right-hand number is simply the first power of 2 down from the left-hand number. For example, let's say the left-hand number is 7. If we go down from 7, we get 6, 5, and 4. 4 is the first power of 2 down from 7. So the hidden number is 4. And therefore, you know that a 7 tuplet is just an abbreviated way of writing a 7 against 4 tuplet. Because of abbreviations, the most common tuplets have even shorter names. For example, a 2 tuplet is called a duplet, a 3 tuplet is called a triplet, a 4 tuplet is called a quadruplet, and so on. Obviously, if you don't abbreviate your tuplet, you can choose whatever numbers you want for both sides. But if you are going to abbreviate your tuplet, you have to follow the 2 rules we just described. An exception to the rules is that a 4 tuplet is commonly written as an abbreviation for a 4 against 3 tuplet. Although this is inconsistent, this is just how people commonly do it. Also, be aware that if you abbreviate a tuplet and the number you do write is 1 or less, you could cause mass confusion. For example, if the left-hand number is 1, then the right-hand number is technically supposed to be 3 halves, which is a little strange. If the left-hand number is between 0 and 1, then the right-hand number will be some other fraction. And if the left-hand number is 0 or less, then there is actually no possible right-hand number, since there are no powers of 2 that are 0 or less. Because of the way tuplet abbreviation works, there are a bunch of abbreviated tuplets that all do the exact same thing. For example, a 3 tuplet just means a 3 against 2 tuplet, so it divides the lengths of its notes by 3 halves. A 6 tuplet just means a 6 against 4 tuplet. 6/4 just reduces to 3 halves. So a 6 tuplet also divides the lengths of its notes by 3 halves. Therefore, a 3 tuplet and a 6 tuplet do the exact same thing. In fact, you can take any abbreviated tuplet and multiply the left-hand number by 2, and the value of the tuplet won't change, because the right-hand number will automatically also multiply by 2. The exact same thing happens with division by 2, but again, it is wise to keep the left-hand number above 1 to prevent confusion. Tuplets have an interesting property known as completeness. To understand what that is, we need to first look at the anatomy of a tuplet. First, we have the bracket. Second, we have the content, which is everything that is under the bracket. Third, we have the value, which is the number inside the bracket, and which tells us what to divide the content by. And fourth, we have the length of the tuplet, which is simply how long the tuplet ends up being. Let's focus on the content for now. This tuplet contains a quarter note, a dotted quarter note, and an eighth note. 1/4 plus 3/8 plus 1/8 equals 3/4. So this tuplet has a content of 3/4. Now, every content inherently has a list of numbers that are called ESDs, or equal standard divisions. An ESD is simply a number of equal parts that you can divide the content into. Now, a number only counts as an ESD if you can notate one of these parts without using tuplets. For example, a content of 3/4 can be divided into 3 equal parts. Each part has a length of 1/4. Now, can we notate a length of 1/4 without using tuplets? Yes, we just write a quarter note. Therefore, a content of 3/4 has an ESD of 3 because we can divide it into 3 parts that can be notated without tuplets. Another example, a content of 3/4 can be divided into 4 equal parts. Each part has a length of 3/16. Now, can we notate a length of 3/16 without using tuplets? Yes, we just write a dotted eighth note. Therefore, a content of 3/4 also has an ESD of 4. Another example, a content of 3/4 can be divided into 5 equal parts. Each part has a length of 3/20. Now, can we notate a length of 3/20 without using tuplets? No, there's no way to do it. Therefore, a content of 3/4 does not have an ESD of 5. Now that we've established that, let's look at the tuplet value. Remember that since the value is simply a horizontal fraction, we can multiply both sides of it by the same number without changing the value. Multiplying both sides of a tuplet value by the same number is called scaling. And remember, scaling does not change the value of the tuplet. There are 2 rules for a tuplet to have completeness. Rule 1. The left-hand number must be an ESD. Rule 2. The right-hand number must be a whole number. If a tuplet satisfies both rules, or it is possible to satisfy them using scaling, then the tuplet is considered complete. If it is impossible to satisfy both rules, even using scaling, then the tuplet is considered incomplete. For example, here we have 4 eighth notes, a dotted eighth note, and a 16th note, all under a 3 tuplet. If we add all of these notes up, we find that the content is 3/4. 3/4 can be divided into 3 equal parts. If we do this, each part has a length of 1/4, and a 1/4 note can be notated without using tuplets. Therefore, the content has an ESD of 3. The left-hand number is 3, which is the same as the ESD. And the right-hand number is 2, which is a whole number. Therefore, because both rules are satisfied, this tuplet is a complete tuplet. Now, what if we remove the last 2 notes from the content, leaving us with only the 4 eighth notes? Now our content is only 1/2. 1/2 can be divided into 3 equal parts. If we do this, each part has a length of 1/6. However, we cannot notate a 1/6 note without tuplets. It's just impossible. If the content is 1/2, dividing into 3 equal parts isn't going to work. The only ESDs we can get are powers of 2. But if we go over to the tuplet value and scale it so that the left-hand number is any power of 2, then the right-hand number will never be a whole number. Therefore, since it's impossible to satisfy both rules, even using scaling, this tuplet is an incomplete tuplet. Some people like to write miniature note values into the tuplet value. For example, like this. These are called quantified tuplets, and the miniature note values are called quantifiers. The reason for doing this goes back to the same idea we expressed earlier, where the colon really just stands for the phrase, in the place of. To convert a quantified tuplet into a normal tuplet, follow 3 steps. Step 1. If only one side has a quantifier, put that quantifier on the other side as well. 2. Replace each quantifier with its fractional form. 3. Multiply the numbers together on each side. For example, here we have a tuplet value indicating 5 dotted quarter notes in the place of 3 half notes. both sides have a quantifier, so we can skip step 1. For step 2, we replace the dotted quarter note with 3/8, and we replace the half note with 1/2. For step 3, we multiply 5 by 3/8 to get 15/8, and we multiply 3 by 1/2 to get 3/2. Now we see that the true value of our tuplet is 15/8 against 3/2. Now, if we wanted to simplify this further, we can do a little algebra. Multiply both sides by 8, simplify the fraction on the right, then divide both sides by 3. So the true value of this tuplet is 5 against 4, which can be abbreviated to simply 5. Therefore, a 5 dotted quarter notes against 3 half notes tuplet is simply a cumbersome way to write a 5 tuplet. Most people also combine tuplets. If you have multiple tuplets that are right next to each other, and their values are the same, you can use one big tuplet to cover the same notes and rests, instead of multiple smaller tuplets. Therefore, our previous example can be simplified to this. Extending a tuplet over a bar line, like this, is not very common, but it is possible. Sometimes you will see tuplets that are on top of each other, like this. These are called nested tuplets. To analyze them, the process is exactly the same. Just divide each note or rest by each of the tuplets that is above it. In this example, the first 2 quarter notes only have 1 tuplet above them. We know that a 3 tuplet really means a 3 against 2 tuplet. So we divide each of these quarter notes by 3/2, and they become 1/6 notes. The next 2 notes, however, are each under 2 tuplets. As for the 5 tuplet, we know that that really means a 5 against 4 tuplet. So we divide each of these quarter notes by 3/2, and then by 5/4. 1/4 divided by 3/2 is 1/6, and 1/6 divided by 5/4 is 2/15. So these 2 notes are 2/15 notes. Finally, the last note is under only the 5 against 4 tuplet. 1/4 divided by 5/4 is 1/5, so the last note is a 5th note. Now, nested tuplets are technically unnecessary, since we only need 1 tuplet to change the length of a note to whatever we want. So, if you ever want to convert nested tuplets into a single tuplet, just go through the passage 1 note at a time. For each note, look at all the tuplets that are above it and multiply their values together to get a product. Then you can replace all of those tuplets with a single tuplet using that product as its value. In our previous example, the first note is under only 1 tuplet, so there's nothing to collapse here. The second note is the same as the first. The third note, however, is under 2 tuplets. The tuplets have values of 3/2 and 5/4. 3/2 times 5/4 equals 15/8. Therefore, for the third note, you can replace the nested tuplets with a single tuplet, using 15 against 8 as its value. You can do the same thing for the fourth note. In addition, as we learned earlier, you can simplify further by combining adjacent tuplets that have the same value. Finally, since 8 is the first power of 2 down from 15, we can abbreviate this tuplet value by writing only 15. Some people also like to imply tuplets by using irrational meter. In this mode of thinking, they will say that if the denominator of the time signature is not a power of 2, then every note and rest within that meter has an implied tuplet over it. Now, what is the value of this implied tuplet? Well, the left-hand number of the tuplet is the denominator of the time signature, and the right-hand number is the first power of 2 down from the left-hand number. Therefore, the implied tuplet can also be an abbreviated tuplet. For example, if I'm in 4/4 meter for 2 measures, I can fill up each measure with 4 quarter notes. If, for the first measure only, I change the time signature's denominator from 4 to 5, then a 5 tuplet is implied over all the notes in that measure. The fact that the denominator is not a power of 2 acts as a length changer for all the notes and rests within the meter. So this first measure actually goes by faster than the second measure. Now, I personally resist this mode of thinking, because now, what looks like a quarter note is actually a fifth note. Using implied tuplets, an irrational meter just changes all of its notes so that they make sense within the meter, which means it really isn't irrational anymore. It's just a different tempo. Plus, if I wanted to put an actual quarter note, I'd have to write a 4 against 5 tuplet over it to cancel out the implied 5 against 4 tuplet. So I personally do not use implied tuplets and will not use them in the following example. If you really want to use them, just make sure to explain how they work to your performers. Let's tie everything we've discussed into one final example. Let's say I've got 6 dotted quarter notes under a 7 tuplet. How would I notate this in 5/11 meter? To notate any rhythm in any meter, we need to perform 3 steps. Step 1. Perform a C-point analysis of the notes and rests. Step 2. Add in as many bar lines as you need to frame the entire example. In other words, keep adding bar line numbers until the last number in your analysis is a bar line number. Step 3. Notate each of the resulting segments. Alright, let's get into it. The first note begins at 0. The first note is a dotted quarter note, which has a length of 3/8. However, the 7 against 4 tuplet changes its length to 3/14. The remaining notes are the same as the first. And since we're going to fill the remaining space after the last note with rests, let's put an R on the 9/7. Now let's frame the example with bar lines. The first bar line is at 0, the second bar line is at 5/11, the third bar line is at 10/11, and the fourth bar line is at 15/11. Now let's find the lengths of all the segments. The first segment is a 3/14 note, the second segment is also a 3/14 note, the third segment is a 2/77 note, the fourth segment is a 29/154 note, the fifth segment is a 3/14 note, the sixth segment is a 4/77 note, the seventh segment is a 25/154 note, the eighth segment is a 3/14 note, and the ninth segment is a 6/77 note. Now, let's figure out how to notate all of these segments. The first segment needs a changed length of 3/14. An easy way to choose a normal length is by replacing the denominator of the changed length with the first power of 2 down from it. The denominator of the changed length is 14. The first power of 2 down from 14 is 8. So our normal length is 3/8. Then we solve for the tuplet value and discover that a 3/14 note can be written as a dotted quarter note with a 7 against 4 tuplet over it. And because 4 is the first power of 2 down from 7, the tuplet can be abbreviated to a 7 tuplet. Using the exact same procedure, the second segment can be written the same way. For the third segment, since the changed length is 2/77, we can pick 2/64 for the normal length. 2/64 reduces to 1/32. Then we can solve for t, and therefore write a 1/32 note with a 77 against 64 tuplet over it, which can be abbreviated to a 77 tuplet. Now, because the segment ends with a bar line, that means the actual note continues past the bar line, so we need to tie the segment to the next segment. For the fourth segment, the changed length is 29/154, so the normal length is 29/128. Therefore, we can tie together 29/128 notes under a 154 against 128 tuplet. Since we might not want to do this, we can combine the first 16 of them into an 8th note. We can combine the next 8 of them into a 16th note. And we can combine the next 4 of them into a 32nd note. Plus, we can combine the 8th note, 16th note, and 32nd note into a double-dotted 8th note. Now, if we still don't like this, we can just use a simpler normal length. Let's just pick a quarter note. If the changed length is 29/154 and the normal length is 1/4, then the tuplet value is 77/58. So, if you prefer, you could also notate the segment as a quarter note under a 77 against 58 tuplet. For the fifth segment, the changed length is 3/14 again. For the sixth segment, we realize that it is exactly twice as much as the third segment. So we can just copy the third segment and double the note value, from a 32nd note to a 16th note. Now, because this segment ends with a bar line, that means the actual note continues past the bar line. So we need to tie the segment to the next segment. For the seventh segment, we can notate a 25 1/54 note as a quarter note under a 77 against 50 tuplet. For the eighth segment, the changed length is 3/14 again. For the ninth segment, we realize that it is the same as the sixth segment, plus half of its value. So, we can just copy the sixth segment and add a dot to the 16th note. And since the last segment is indicated as a rest, we change the dotted 16th note to a dotted 16th rest. And there we go. Alright, I hope this video has helped you. If it has helped you, don't forget to leave a like. If you have any questions, let me know down below. If it's a simple question, I'll update the description with an answer. If it's more complicated and enough people ask it, I'll make a video about it. Thanks for watching.